Hello again. Here's another summary video for Diploma Programme Physics. This time I'm going to talk about topic 5.2, which is about the heating effect of electric currents. Firstly, let's talk about circuit diagrams, which you should be able to draw yourselves and interpret. This is the circuit symbol for a battery or electric cell. The long line is the positive side and the short one is the negative side, and conventional current goes from positive to negative. Black lines indicate wires, and a rectangle like this is a resistor. A rectangle with a line through it is a variable resistor. And if we want to measure the current in the circuit, we place the ammeter in series with the component we want to measure the current for, and voltmeters are connected in parallel, which means across a component like this. Dots in a circuit sometimes symbolize junctions. Now here's another quantity that we'll need to define, and that's one of resistance, which is often confused with Ohm's law, but the quantity of resistance is defined simply as the ratio of potential difference to current, and that's basically V divided by I. The unit is the ohm, which is this Greek letter here, capital omega. Now, in terms of resistance, if I was to vary the resistance in this circuit and therefore vary the potential difference and measure the current in the circuit, then if a component's current is proportional to its potential difference, we say that it's an ohmic conductor. That's the blue line here. So if a straight line graph can be plotted through the points and through the origin, then it's an ohmic conductor. However, if there's any other situation, i.e. this conductor which has a curved IV characteristic, we call it, then it's a non-ohmic conductor. And some examples of ohmic conductors are ordinary ceramic resistors you get in the lab, and an example of a non-ohmic conductor is a filament bulb. Now, in terms of the heating effect, what's happening in a resistor is electrical energy is getting converted to thermal energy, and heat is being given off. So we say the power dissipated, capital P, is simply, and I won't do the definition, but it's voltage times the current. And there are two other forms of this expression. The power dissipated can also be the square of the current times resistance, or the square of the potential divided by resistance. All conductors have a so-called resistivity, which is proportional to their resistance. So a conductor with a large resistivity is going to have a large resistance. And normally in circuits we use copper because it has a low resistivity. And in a conductor, there's a formula for resistance in terms of resistivity, which is R equals rho L over A, where rho is the resistivity in ohm meters, capital L is the length of the conductor, and capital A is the cross-sectional area. So if I was to have a smaller cross-sectional area, that would give me a larger resistance. If I was to have a longer length of wire, then I'd have a larger resistance, and a larger resistivity would give me a larger resistance. Finally, in this subtopic, we have to talk about Kirchhoff's laws. And there's two important concepts basically to understand Kirchhoff's laws, and that is that we have conservation of energy and conservation of charge. So in a loop, this is what's called a multi-loop circuit, where we connect on a cell and a resistance to the bottom, or in parallel with a top circuit. In any one loop, we have conservation of energy or potential difference. So the sum of all the potentials in a loop has to add up to 0. And at any junction, charge is conserved. So the charge going into the junction has to equal the charge going out. So look at this example multi-loop circuit. We have a top loop with a cell PdV1, we have a resistance R1, then we have a middle section with a resistor R2, then connected up again to the cell again. In parallel with the top circuit, we have a bottom section with a resistance R3 and a cell V2 connected like this. And we make our loop arbitrarily from one point going, in this case, anti-clockwise around here, and in this case the bottom loop is going clockwise. It's up to you which direction you make the loop, but it's easier to make the loop go from negative to positive across the cell, because then that gives you positive potentials for the cell. So in terms of Kirchhoff's junction law, if we look at this junction here, the two currents going into the junction are I1 and I3. So I1 plus I3 must equal I2. In the top loop, going across the cell here, we have positive V1 minus I1 R1, because if the loop's going in the same direction of the current, then we're losing energy. Then we have a negative here. And because V equals IR, the voltage drop across here, if you like, is I1 R1. Then in the middle section we have to subtract I2 R2 before we're back to the start of our loop, and all of that has to equal 0 due to conservation of energy. And then similarly from the bottom loop, change the direction of my loop to make me go across from the negative to positive of the cell down here. I get V2 minus I3 R3 minus I2 R2, because this section is common to both loops, equals 0. So we have a system of simultaneous equations that, if we're given enough variables, we can solve for 3 unknowns. 3 equations means we can solve for 3 unknowns, but if we're given too few unknowns, then we cannot solve the equation.